Let's review lists and list mutation operations. Assume for each of the following examples that we've already set S to the list 2, 3 and T to the list 5, 6, and we'll keep doing that over and over again for each example. Here are all the different list mutation operations, an example for each one, and the result of executing that example. Append adds one element to a list. If I append T to S, I will append as an element to S the list T. This rebinds the name T to 0 as opposed to the list that it used to be bound to. But that list is still part of S. Here's the result. 2, 3, and then the list 5, 6 are the three elements in S. T is bound to 0. Extend is like append, except for that instead of taking an element, it takes a list of elements, and it adds all those elements in one list to another list. So s.extend T builds the list 2, 3, 5, 6 without any nesting structure. If T is changed afterwards, those elements are already added to S and will not be affected. So the result is 2, 3, 5, 6, and then T was 5, 6, but we changed the 6 to a 0, so now T is 5, 0. Addition between lists, when you take one list and add it to another, as well as slicing a list, both create new lists containing existing elements. For this, we'll do a longer example. Here we take A, a new name, and bind it to S plus a list containing T. Then we set B to a slice of A starting at index 1 and going to the end. If you omit the second index, then it goes all the way to the end. If we had omitted the first index, we would have gone all the way to the beginning. Here we change A1 to 9 and B1, 1 to 0. Let's walk through the environment diagram on this one. In the beginning, S is bound to 2, 3, and T is bound to 5, 6 because we've executed these two lines. Then we bind A to S plus list containing T. So for a brief moment, we did build a list whose contents was this list, but the only reason we did that was to add it to this list S. And addition creates a new list with all the elements of S followed by all the elements of the list containing T. The element in the list containing T is the list T, this list. So now we have a list within a list, much like we did back here. But this one isn't called S, it's called A. Then we set B to a slice of A. Starting at index 1 onward means that we create a new list that contains this 3 and this list. So both the element at index 2 and the element at index 1 are T. Now we're going to perform some changes. A1 equals 9, we look in A, find index 1, change this to a 9. B11 equals 0, we find element at index 1 of B is this list. The element at index 1 of this list is going to be changed to 0. That is going to affect A, B, and T when we print them out. So the results are that S is the list 2, 3, T is 5, 0, A is 2, 9 with the list 5, 0 in it, and B is 3 with the list 5, 0 in it as well. When you just print these things out, you can't tell that these are the same list over and over again, and that's why we use environment diagrams with box and pointer notation. The list function also creates a new list containing existing elements. So if I say T equals list S and then set S1 to 0, T is a separate list containing the contents 2, 3 that were in S when this expression was evaluated. Then later, the list S was changed, but T was not changed. And finally, slice assignment, perhaps the trickiest one of all, replaces a slice with new values. If I set S from 0 to 0 to T, what that's doing is inserting the contents of T into S at a particular position, replacing a slice. Now this is an empty slice. When you replace an empty slice, you're inserting the elements in T into where this slice would be in order. So this says put the elements 5, 6 in here, position 0, and since this is an empty slice, we're not really replacing anything. So the result will be 5, 6, 2, 3. Now this says, with 5623, replace index 3 onward. 5623's element at index 3 would be the 3. We're replacing everything from there onward with the contents of T, which again is 56. And so the result is 56256. Changing T after performing this slice assignment will not change S because we've copied the contents from T into S. Okay, now we know the rules. Let's look at some examples from past exams. Here's one. It says T starts out as the list 1, 2, 3. Then we'll perform slice assignment to set it equal to a list containing T. And then we'll extend T with T. Let's go through it. The first line says T is bound to the list 1, 2, 3. With slice assignment, just like regular assignment, we need to evaluate what's on the right-hand side of equals. And list T evaluates to a new list containing T. Slice assignment will replace this slice, the elements index 1 through 3, with the contents of this list. The contents of this list is T. Notice that since we've removed index 1 and 2, the index of this is 1. Next we do T.extend T. What this does is extend T with whatever the contents of T are now. So this would put a 1 and a reference to T into T, and there's that extension. 1 is added and this value is added. This value happens to be a reference to this whole list. And now we're done. If I were to print out T at this point, here's what Python would display. It would display the contents as 1, and then a self-reference, and then 1, and then a self-reference. Okay, let's move on to this next example. T is the nested list with 1, 2, and 3, 4. Here's a box and pointer diagram. T has 2 elements, the list 1, 2, and the list 3, 4. We're going to find T0, that's this list. We're going to append to it the result of slicing from 1 to 2, T. Here's T. The slice from 1 to 2 is this element only in a new list. That's what slicing does. So here's a new list with that element in it. That element is the list 3, 4. And then what do? We append it to T0. So that means inserting a new element in T0 that is this list. And now we're done. If we were to print that out, it would look like this. A list with 2 elements. The first element is a list 1, 2, and then a list containing 3, 4. And the second element is the list 3, 4.